Imagine waking up tomorrow to a universe that looks exactly the same, except for one impossible fact. Jupiter is gone. No explosion, no debris, no warning. The largest planet in our solar system simply disappears. If that thought makes you uneasy, hit like right now, because what happens next is not science fiction. It is orbital mechanics. Jupiter is not just another planet. It contains more than twice the mass of all the other planets combined. Its gravity shapes the architecture of the solar system. It bends asteroid paths, stabilizes orbital resonances, and influences the motion of planets across billions of kilometers. Remove it, and the gravitational balance shifts instantly. At the very moment Jupiter vanishes, nothing explodes. Earth does not lurch out of orbit, the sun does not flare, but every object in the solar system immediately begins responding to a new gravitational equation. For billions of years, Jupiter's mass has pulled subtly on everything around it. Without that pull, the delicate choreography of orbital motion begins to adjust. The first region to feel the change would be the asteroid belt. Located between Mars and where Jupiter used to orbit, this region is not a dense wall of rocks, but a gravitationally sculpted structure. Jupiter's massive presence creates gaps, clusters, and resonances within the belt. Those patterns exist because of Jupiter. Remove it, and those resonances weaken. Over time, asteroid orbits begin drifting. Some asteroids would move into slightly more elliptical paths. Others would shift inward or outward. These changes would not happen in seconds, but they would begin immediately. Tiny deviations compound over time. What looks stable today becomes unpredictable over thousands or millions of years. Meanwhile, the outer planets would begin a slow gravitational rebalancing. Saturn, Uranus, and Neptune are locked in long-term interactions influenced by Jupiter's mass. Without the largest gas giant anchoring that system, subtle shifts in orbital resonance begin propagating outward. The solar system does not collapse, it evolves. Closer to home, Earth continues orbiting the Sun almost exactly as before. The Sun's gravity dominates our motion, but Jupiter still contributes a measurable influence. Over long timescales, the absence of that influence could slightly alter Earth's orbital eccentricity and tilt cycles. Climate patterns governed by Milankovitch cycles could slowly change. If you're still watching, here's the key point. Jupiter's disappearance would not cause immediate catastrophe. It would trigger a long gravitational domino effect. The solar system would not explode. It would slowly rewrite its own structure. And that is only the beginning of the story. The asteroid belt would be the first major region to feel the full consequences of Jupiter's disappearance. Today, the belt is not random. It is shaped by gravitational resonances created by Jupiter's enormous mass. Certain orbital periods are stable, others are forbidden. These gaps, known as Kirkwood gaps, exist because Jupiter repeatedly tugs on objects whose orbital timing matches specific ratios. Over millions of years, those repeated tugs clear out entire zones. Remove Jupiter, and those resonances vanish. At first, nothing dramatic happens. The asteroids keep moving along their established paths. But those paths were sculpted under a gravitational regime that no longer exists. Without Jupiter's stabilizing and destabilizing influence, small gravitational interactions between asteroids begin to matter more. Collisions slightly alter trajectories. Minor deviations accumulate. Over thousands of years, the belt becomes less structured. Some objects drift inward toward Mars-crossing orbits. Others migrate outward. The clean gravitational architecture that once maintained semi-stable lanes begins to blur. The asteroid belt does not explode outward in a cinematic storm. It becomes dynamically looser. And here is where Earth enters the equation. Jupiter has long acted as a gravitational filter. It deflects some comets and asteroids away from the inner solar system. It also sends some inward. Its role is complex. It is not simply a shield, but its mass strongly influences which objects remain in the outer solar system and which are redirected inward. Without Jupiter, the long-term flux of asteroids into near-Earth space would change. Some studies suggest that, initially, the inner solar system might experience fewer direct perturbations from Jupiter-driven injections. However, over longer timescales, the destabilized asteroid belt could gradually feed more objects inward through chaotic interactions. The critical detail is time. Within the first year, nothing noticeable changes in the night sky. Within the first century, astronomers begin detecting unusual orbital shifts in certain asteroid families. Within a few thousand years, impact probabilities for inner planets begin to diverge from current models. This is not an immediate apocalypse. It is a slow increase in unpredictability. Mars, positioned closer to the belt, would feel the early effects more strongly than Earth. Increased asteroid crossings could alter its already unstable climate cycles. Impacts on geological timescales might become more frequent. Earth's risk profile would evolve more gradually. If you are still watching, understand this. Jupiter does not simply sit beyond the asteroid belt as decoration. It actively maintains structure through resonance. Remove it, and gravitational order becomes softer, less constrained, more chaotic. And the asteroid belt is only the beginning, because beyond it lies the realm of Saturn, Uranus, and Neptune, a region whose long-term stability depends on a delicate balance of giant planet interactions. Without Jupiter, that balance begins to shift in ways that take millions of years to fully reveal themselves.
Beyond the asteroid belt, the outer solar system appears calm and distant. Saturn, Uranus, and Neptune orbit the Sun in vast, slow paths measured in decades and centuries. Yet their motions are not independent. They're linked through long-term gravitational resonances, and Jupiter plays a central role in that balance. Jupiter and Saturn, in particular, share a deep dynamical relationship. Their orbital periods form near-resonant ratios that subtly influence each other's eccentricity and inclination. Over millions of years, this interaction stabilizes the architecture of the giant planet system. Remove Jupiter, and Saturn immediately becomes the dominant gas giant. At first, Saturn continues on its established orbit. The Sun's gravity still dictates the primary motion of every planet. But without Jupiter's counterbalancing mass, the gravitational field in the outer solar system becomes less symmetrical. Saturn's orbit would slowly adjust. Tiny changes in eccentricity would begin accumulating. Uranus and Neptune, which are already involved in complex resonant interactions, would feel that adjustment. Orbital mechanics is unforgiving but gradual. A change of even a fraction of a percent in eccentricity can, over millions of years, shift planetary distances by millions of kilometers at perihelion or aphelion. These are not human timescale changes. They unfold across epochs. Computer simulations of planetary systems show that removing a dominant gas giant often increases long-term instability. The system does not collapse immediately, but chaotic zones widen. Over tens of millions of years, Uranus or Neptune could experience amplified eccentricity variations. Their gravitational influence on trans-Neptunian objects would evolve accordingly. And this brings us to the Kuiper Belt. Beyond Neptune lies a vast population of icy bodies. Many of their orbital structures are indirectly shaped by the presence of Jupiter and the giant planets. Remove Jupiter, and the chain of gravitational interactions subtly shifts. Neptune's dominance in the outermost regions becomes slightly more pronounced. Over immense spans of time, orbital distributions in the Kuiper belt could rearrange. Would any planet be ejected from the solar system? Not immediately. The sun's gravity overwhelmingly dominates. But stability is a spectrum, not a switch. Planetary systems without a dominant inner gas giant often show greater long-term chaotic behavior in simulations. If you are still watching, here is the key. Jupiter is not just large, it acts as a stabilizing mass in a multi-body gravitational web. Remove one node in that web, and tension redistributes across the entire structure. The solar system would not shatter, it would enter a new evolutionary phase. And that evolution would not be confined to the outer planets, because over long timescales, changes in the giant planet configuration can influence the inner solar system, including Earth's axial tilt cycles and climate stability. The disappearance of Jupiter would echo inward slowly but persistently. And that inward echo is where the story becomes personal.
At first glance, Earth seems safe. The Sun contains more than 99% of the solar system's mass, and its gravity overwhelmingly controls our orbit. Jupiter's pull on Earth is small compared to the Sun's influence. So if Jupiter vanished, Earth would not suddenly spiral outward or plunge toward the Sun. But gravitational systems are not about dominance alone. They're about long-term interactions. Jupiter contributes to subtle variations in Earth's orbital eccentricity, how circular or elliptical our orbit becomes over time. It also influences long-term cycles in axial tilt and precession. These variations, known as Milankovitch cycles, affect climate patterns over tens of thousands of years. Without Jupiter, those cycles would not stop. They would change. Computer models suggest that removing a massive gas giant can alter the amplitude of eccentricity oscillations in inner planets. Earth's orbit might become slightly more circular over certain epochs, or slightly more elliptical over others. Even small percentage changes in orbital eccentricity can modify how much solar energy different parts of the planet receive seasonally. Over thousands of years, that could shift glacial cycles. Jupiter also plays a role in limiting chaotic orbital interactions among inner planets. Its gravitational presence helps constrain resonances between Mars and Earth. Remove it, and the long-term orbital coupling between the terrestrial planets subtly evolves. Mars is especially sensitive. Its orbit already varies more dramatically than Earth's. If Mars's eccentricity increases further over millions of years, gravitational interactions between Mars and Earth could become slightly stronger. Not enough to cause collisions, but enough to influence orbital oscillations. The key word is amplification. Small gravitational differences compound over immense timescales. Over tens of millions of years, Earth's orbital stability might decrease slightly. Climate patterns tied to orbital forcing could become less predictable. Ice ages might arrive earlier or later relative to current cycles. None of this happens tomorrow. None of it is visible in a single human lifetime. But planetary stability is measured in millions of years, not decades. And there's another dimension. Jupiter influences the rate at which long-period comets from the outer solar system enter the inner regions. Without its gravitational perturbations, the distribution of comet trajectories would shift. Some would be less likely to enter sun-grazing paths. Others might slowly drift inward through different chaotic channels. Impact probability does not vanish, it evolves. If you're still watching, understand this. Earth's safety is not guaranteed by the Sun alone. It emerges from the combined gravitational architecture of the solar system. Remove Jupiter, and Earth continues orbiting, but within a subtly altered system. Over geologic time, that alteration matters. The disappearance of Jupiter would not create instant destruction. It would begin a slow rewrite of orbital history, a quiet adjustment whose consequences would unfold long after the event itself. And the deeper we look into long-term dynamics, the more profound those consequences become.
Beyond Neptune lies a vast reservoir of icy bodies known as the Kuiper Belt, and much farther out, the Oort cloud. These distant regions contain trillions of cometary nuclei, frozen remnants from the solar system's formation. Most remain far from the Sun for billions of years, but occasionally gravitational disturbances send them inward. Jupiter plays a decisive role in that process. As the most massive planet after the Sun, Jupiter acts as a gravitational gatekeeper. When long-period comets fall toward the inner solar system, Jupiter's gravity can do several things. It can deflect them outward, ejecting them entirely. It can redirect them into shorter-period orbits, or it can send them inward toward the terrestrial planets. Jupiter is not simply a shield, it is a traffic controller. Without Jupiter, the gravitational landscape changes immediately. Comets entering from the outer solar system would no longer encounter a dominant inner gas giant. Their paths would instead be influenced primarily by Saturn and, to a lesser degree, the terrestrial planets. At first, this might reduce the dramatic slingshot effects Jupiter creates. Some comets that would have been redirected inward by Jupiter's strong gravity might instead pass more smoothly through the outer solar system. That could temporarily decrease the rate of short-period comet formation. But over longer timescales, the absence of Jupiter's stabilizing influence on Saturn and Neptune would reshape the gravitational architecture of the outer regions. Subtle orbital shifts among the giant planets could alter the resonance structures that help confine trans-Neptunian objects. And that is where unpredictability grows. Small changes in Neptune's orbit, even measured in fractions of a percent, can modify resonance zones in the Kuiper Belt. Over millions of years, more objects might drift into unstable trajectories. Some could be nudged inward, gradually increasing comet flux toward the inner solar system. The Oort cloud adds another layer. Passing stars and galactic tides already disturb its outer edges. Jupiter's gravity helps shape the trajectories of comets that fall inward from that vast sphere. Remove it, and the filtering mechanism changes. Would Earth face more impacts immediately? No, the solar system operates on timescales far beyond human history. But impact probability curves would evolve. Over tens of millions of years, Earth's collision risk profile might diverge significantly from its current baseline. If you are still watching, this is the central theme. Jupiter does not simply block threats, it shapes the entire distribution of small bodies. Its presence determines which objects remain distant and which migrate inward. Without it, the solar system does not become instantly more dangerous or instantly safer, it becomes dynamically different. And in orbital mechanics, different often means less predictable. The disappearance of Jupiter would transform not just the motion of planets, but the long-term rhythm of cometary encounters that have shaped Earth's geological and biological history. And those rhythms matter more than we often realize. With Jupiter gone, Saturn instantly becomes the most massive planet in the solar system. But Saturn is only about 1/3 as massive as Jupiter. That difference is enormous in gravitational terms. The outer solar system would not simply continue as before, with Saturn taking Jupiter's place. The balance would shift fundamentally. Jupiter currently dominates the gravitational hierarchy beyond the asteroid belt. Its mass shapes resonance chains that extend across vast distances. Saturn participates in those chains, but always in interaction with Jupiter. Remove Jupiter, and Saturn loses its primary gravitational partner. Initially, Saturn's orbit remains nearly unchanged. The Sun still controls its primary motion, yet the subtle gravitational tug that Jupiter exerts on Saturn vanishes instantly.
Over time, this absence alters Saturn's orbital eccentricity. The small oscillations that once resulted from Jupiter-Saturn interactions begin damping or reshaping. Uranus and Neptune feel that difference. In the current solar system, the giant planets exist in a delicate web of gravitational resonances. These resonances help prevent chaotic orbital drift over billions of years. Computer simulations show that multi-planet systems can remain stable only if certain mass ratios and orbital spacings are maintained. Remove the largest mass in that configuration, and the resonance pattern changes. Saturn's gravitational influence on Uranus would gradually become more dominant. Over millions of years, Uranus's eccentricity might increase slightly. Neptune's orbit could shift in response. These changes are subtle but cumulative. Planetary systems are sensitive to initial conditions. Even tiny variations can amplify across millions of years through chaotic diffusion. The solar system is remarkably stable, but not perfectly rigid. Its stability depends on its current mass distribution. Without Jupiter, Saturn cannot fully replicate its stabilizing role. The gravitational landscape becomes less anchored. Over tens or hundreds of millions of years, the probability of significant orbital rearrangement increases slightly. Would planets collide? The likelihood remains low on short timescales, but long-term stability simulations indicate that removing a dominant gas giant can increase chaotic zones. Uranus and Neptune could experience more pronounced orbital oscillations. Their influence on the Kuiper belt would evolve accordingly. If you are still watching, consider this. Planetary systems are not static sculptures. They are dynamic gravitational ecosystems. Mass matters. Ratios matter. Distance matters. Jupiter's mass is not interchangeable. Saturn, though majestic and massive, lacks the gravitational strength to impose the same order. The disappearance of Jupiter would reduce the solar system's central stabilizing force beyond the inner planets. And as outer planet stability softens, the slow ripple of gravitational adjustment continues propagating inward. The question becomes not whether something dramatic happens immediately, but whether the solar system's long-term calm is as permanent as it appears. Without Jupiter, that calm becomes slightly more fragile, and fragility, on cosmic timescales, eventually expresses itself. On human timescales, the disappearance of Jupiter would seem almost anticlimactic. The sky would look the same, the sun would rise and set, Earth would continue orbiting as usual. But planetary stability is measured in millions and billions of years, and over those timescales, even small gravitational changes can produce dramatic outcomes. The solar system today is considered dynamically stable. That does not mean nothing changes. It means that large-scale, catastrophic rearrangements are unlikely within billions of years under current conditions. This stability is partly the result of the existing mass distribution, especially Jupiter's mass. When astrophysicists simulate planetary systems without a dominant gas giant, they often observe increased orbital diffusion. Eccentricities grow slowly, inclinations fluctuate, resonances weaken or shift. Chaos does not erupt instantly, it creeps. Without Jupiter, long-term simulations suggest that the inner planets could experience slightly larger variations in orbital eccentricity. Mars, already the most dynamically sensitive terrestrial planet, might undergo amplified oscillations. Its orbit could become more elliptical over extended periods, influencing gravitational coupling with Earth. These amplified variations would not cause collisions in the near term, but chaotic systems have thresholds. When eccentricity increases beyond certain values, orbital crossings become more probable. Over hundreds of millions of years, the statistical likelihood of extreme events rises. The outer solar system would also evolve differently. Saturn's modified resonance relationships with Uranus and Neptune could produce slow orbital migration. Even a small outward or inward drift measured in fractions of an astronomical unit over vast timescales can reshape resonance chains. The Kuiper belt would gradually redistribute. Some populations might become more unstable. Comet injection rates toward the inner solar system could fluctuate in new patterns. The solar system would not become wildly unstable overnight, but its long-term predictability would decrease. If you are still watching, here is the deeper truth. Planetary systems are delicate arrangements born from chaotic beginnings. Our solar system formed through violent collisions and migrations. It reached its current configuration after billions of years of gravitational negotiation. Jupiter's mass played a central role in that process. Remove it, and the solar system does not revert to chaos immediately, but it becomes slightly less resistant to it. The key word is probability. Over the next million years, little changes. Over the next 100 million years, orbital deviations accumulate. Over 1 billion years, those deviations could reshape the architecture in ways difficult to predict precisely. Would Earth survive? Almost certainly for immense spans of time, but the long-term stability envelope narrows. The solar system without Jupiter becomes more sensitive to perturbations from passing stars, galactic tides, and internal resonances. And that means its future becomes more uncertain. The disappearance of Jupiter would not be a dramatic explosion. It would be the quiet beginning of a slower, more chaotic evolution, one that unfolds beyond any human lifetime, yet fundamentally alters the destiny of our planetary system. And that brings us to the final question.
So, what would the solar system ultimately become without Jupiter? Not a disaster, not a firestorm, not an immediate collapse. Instead, it would become something quieter and more unpredictable, a system without its central gravitational anchor beyond the Sun. Jupiter's importance is not obvious when you look at the sky. It appears as a bright point of light, one planet among many. But in terms of mass distribution, it dominates everything except the Sun. Its gravitational presence shapes orbital resonances, sculpts the asteroid belt, influences comet pathways, and stabilizes the delicate dance of giant planets. Without it, the solar system continues, but differently. In the first 1,000 years, astronomers would detect subtle orbital deviations. In 1,000,000 years, statistical models of asteroid impact probability would begin diverging from current predictions. In tens of millions of years, outer planet resonances would soften and shift. In hundreds of millions of years, the architecture of the solar system might look measurably altered. The Sun remains the master of gravity. That does not change. But the Sun alone does not guarantee order. Order emerges from how mass is distributed across space. If you are still watching, understand this. Stability is not the absence of motion, it is the balance of motion. Jupiter contributes massively to that balance. Would Earth survive? Yes, for immense spans of time, but Earth's long-term orbital oscillations might increase slightly. Climate cycles tied to orbital variations could shift. Impact probabilities could evolve. The solar system's future would become less constrained by the strong resonance network that currently exists. There is another perspective to consider. Many exoplanet systems discovered around other stars contain massive gas giants close to their suns or in highly eccentric orbits. Those systems often appear dynamically chaotic compared to ours. The relative calm of our solar system may be partially due to Jupiter's mass and position. Remove it, and we edge closer to a less ordered configuration. The disappearance of Jupiter would not rewrite the solar system overnight. It would begin a new gravitational chapter, one defined by slow divergence rather than sudden catastrophe. And that may be the most unsettling idea of all.
because when we think of cosmic threats, we imagine explosions, collisions, dramatic endings. But sometimes the most profound changes begin silently, invisibly, with equations adjusting across billions of kilometers. Jupiter is not just a planet, it is a stabilizing force woven into the structure of our system. Take it away, and the solar system does not end. It evolves into something slightly more fragile, slightly more chaotic, and far less predictable over deep time. And that quiet shift would shape the destiny of everything orbiting our sun.